Welcome back, Math 82 folks. For this video, go to the first page in your notes outlines for Lecture 5, and we will start there. In this video, we are going to continue to learn about two theorems that give us some information about when solutions to an initial value problem or boundary value problem are going to exist. And if that solution exists, we need some guarantee that there is only one solution. That is, the solution is unique. So these theorems don't actually provide for us the solutions, but the good news is they can tell us whether or not it's even worth looking for a solution in the first place, because if the solution doesn't exist, of course, we don't need to look for it. Why do we care about existence and uniqueness? Well, think about a situation in which you are looking for a solution to an ODE numerically. So let's say you ask your program to find a solution to an initial value problem at a point where, in fact, that solution doesn't exist, but we didn't check. It turns out most numerical solvers will be happy to give you an answer to your request, and a number will be spit back out at you. But that solution doesn't even exist. So it's always important to check first that a solution exists before you go chasing after finding it. Now let's take a look at one of our first theorems. When we were in class last time, we did see this theorem 1 for existence and uniqueness that applies to linear ODEs. And what it said was the following. If you take an initial value problem, and remember, every time we say initial value problem, the same thing applies to a boundary value problem. So if you take an initial value problem for a first order linear differential equation, right here, it's key that it's linear. We always have to put it in normal form so that we can use the theorem properly. And we're going to name the coefficients of our normal form first order DE, P of t and Q of t. And we're going to have an initial condition. Of course, we need that initial condition to even have any hope of uniqueness. If those coefficients that we found, P of t and Q of t, are continuous on some interval of time that contains our initial condition, our initial state, then what this theorem tells us is that the solution exists and is unique on that same interval, So that's actually pretty powerful. Let's look at this example that we also saw last time in class. So we won't go through the solution process. So this is just a reminder. If we wanted to know whether this first order linear, non-autonomous, non-homogeneous ODE has a solution and whether that solution is unique, what do we need to do? We need to first write the ODE in its normal form so that we can identify the P and the Q identified for you here. Sine t is P and t squared is Q. Then we determine whether P and Q are continuous. Sine t and t squared are actually both continuous on the entire real line. So they are. So the conditions of theorem 1 are met, which means that we are now guaranteed by theorem 1 that this ODE has a solution on the entire real line because our P and Q are continuous on the entire real line. Note, by the way, that if you actually want to find the solution to this first order linear, non-autonomous, non-homogeneous differential equation, you are going to have to use the integrating factor technique because the ODE is not separable. If you want to take a second and test yourself and figure out what the solution to that ODE is, you can pause the video now and give it a try. When you come up with your solution, you should ask yourself, does it look like your solution actually does exist and give you a unique value for every value of time on the real line? It should, because our existence uniqueness theorem tells us that it will. If you want to check yourself, if I were to do this, my integrating factor would be e to the cosine t. A general form for your solution might be e to the minus cosine t integral e to the cosine t squared dt, something you'll have to integrate, and plus a constant. But at least you actually have a form for your solution y. All right, let's go to the next page where we can now consider a theorem that can be applied to even a non-linear ordinary differential equation. Still first order, of course. Okay, now for this theorem, we are going to have to remember what it means to take a partial derivative, because that shows up here in our theorem. So when you're taking a partial derivative of something like f, function of f and t and y with respect to just the variable y, as in this case, it means we can treat the other variable t as a constant, just for this case. So let's see what this theorem 2 says, which now can apply more generally. We consider the initial value problem for the first order differential equation. Y prime is some general f of ty. And so here's how the differential equation can be nonlinear. It depends on what f is, with some given initial condition. Now look at f, the right-hand side, and its first partial derivative in y. If both of those functions are continuous in some region of t, of time, and continuous in some region of y, and that region has to contain the place where we start, so our initial time and the initial value of our solution at that point in time, then what does this theorem say? It says that the solution to the initial value problem, or the boundary value problem, exists and is unique on some interval of time surrounding our initial time, t naught, and that interval can be size sum to h. That h and the size of that interval is not guaranteed. So in this rectangle down here, we can see what this looks like. So for t, between two values alpha and beta, and for y, between two values gamma and delta, what this theorem tells us is that for some initial time t naught, we are given an initial value for y. So that's given up front in our initial value problem. So this is our value for y naught, and it sits somewhere in this rectangle. What the theorem tells us is as long as f and its first partial are continuous on this entire rectangle, as long as that's the case, then we know a solution is going to exist in some sub-region. So somewhere surrounding t naught, where this is t naught minus h, t naught plus h, somewhere in here, we know that a solution is guaranteed to exist, somewhere in there. But what it doesn't tell us is what that mysterious h is. In some sense, the theorem is weaker because it doesn't tell us exactly where the solution exists, but it's more general because it includes both linear and nonlinear ODEs. So theorem 2 can be applied to both linear and nonlinear ODEs. However, the result is a bit weaker in that we don't really know exactly where that interval of existence is. We just know that there is one. Okay. One thing that I'd like to point out is that if the conditions of the theorem are not met, that actually does not necessarily mean that solutions don't exist. It just means that the theorem doesn't provide any information. So in other words, theorem 2 is not an if and only if statement. In fact, it just goes in one direction. All right, let's go to the next page and look at an example. This example comes from our homework number 2, problem 3, and we were able to solve this using separation of variables in that homework. So we actually have a solution to this, but it's a nonlinear ordinary differential equation, so we cannot use theorem 1. We can only apply theorem 2 to tell us about the existence and uniqueness of this solution. So to apply theorem 2, we're going to have to put the ODE into normal form. We are going to have to identify then, once it's in normal form, identify what the functions f and its partial derivative are. And then finally, we need to decide in what regions of x and y are those functions continuous. So why don't you pause the video for a second and decide for yourself what the answer is, and then come back. All right, putting this into normal form means we are writing this like dy dx is 1 over y, 1 minus y squared, sine x, which then identifies for us precisely what our function f is. This is our f of xy. And by the way, this is a boundary value problem. Why? Only because our independent variable is x, and so we assume we're working in space, so we call it a boundary value problem. But the process is exactly the same We'd call it an initial value problem if the independent variable were t, and it implies that we are working in time. So I have my f. Now I need to figure out my partial. So the partial of f with respect to x is then, and I won't go through the details because hopefully you can do it yourself, sine x 1 over y squared minus, and then minus 1. So where are these continuous? At least for x, they're continuous everywhere. So f and f sub y, which is the shorthand for partial f partial x, are continuous for all x. However, ideally, you saw a problem for certain y. And of course, that problem is exactly where y is 0 because we do not want to divide by 0. However, there is a discontinuity at y equals 0. So they are not continuous for all y. They're just continuous for all y except at y equals 0. So what that tells us is we can't actually cross
the x-axis.
So if I were to sketch what this might look like in X and Y, and you might want to try this on Desmos to see what you come up with. If my initial condition were positive, so if Y naught is positive, we will have a solution that's completely above the y equals 0 axis. And it will look something like, it's something like this. At space step 0, we have our y0 positive, and we'd have a solution that looks something like this. On the other hand, if y naught is negative, we are below the y equals 0 axis, and it comes down somewhere like this. This would be a y naught negative. So where are our domains of existence for y naught positive? We can say that our x can roam anywhere it wants between minus infinity and infinity. However, y must stay strictly above the value 0.
Analogously, if our initial condition y naught is negative, then our solution y of t can exist only between 0 and negative infinity, but for all values of x.
If you want to go to Desmos and take a look at what this looks like, plot the solution. Y squared equals 1 minus some constant exp of cosine x, and you can actually put in a slider for c, the constant in Desmos, and when c equals 1 over e, you get this situation. In other words, if you start at y naught equals 0, if y naught equals 0, your constant is going to be forced to be 1 over e. All right, so the y naught equals 0 is a problem. What's happening right here? What's happening there is our solution fails to be unique because it's got two different branches. We might be happily walking along here. We hit this point where y naught is 0. And which way do you go? Do you then go this way or do you go this way? So you can see that we have multiple branches and we have lost uniqueness in the case that y naught equals 0. And that is why it is important to check for existence and uniqueness. So I'm going to pause here and we will do more in class together. I'll look forward to seeing you in class. Have a good day. Take care. Bye.